moving on the further lecture, as we've seen, we can perform the linear stability analysis either by the numerical approach or either by the theoretical approach. So in this lecture, we will look at performing the linear stability analysis for the boundary layer flow by using the theoretical approach. And we will consider here for the simplicity an incompressible boundary layer. As we talked about, linear stability is performed on laminar mean flow, which is also referred sometimes as a steady state solution that doesn't change with time, which is also sometimes in the literature referred as base flow or basic flow. Sometimes researchers also use time average mean flow, but this remains a topic of debate since the time average mean flow comes from the time varying flow such as LES or other kind of transient flow. But for now, we will stay out of this debate and we will consider the laminar mean flow, and we perform the linear stability by using the linear stability theory that is reduced to an eigenvalue problem, and this gives solution in terms of alpha, beta, and omega, which are streamwise, spanwise wave number and frequency, and depending on the sign of these variables and their values, we quantify the flow as a stable or unstable. So eigenvalue problem basically gives eigenvalue and eigenvector. Eigenvalue is also known as eigenmode, and eigenvector is basically which we get out of this eigenvalue problem. Those eigenvectors are orthonormal to each other. It means that whatever the eigenvector we get out of this eigenvalue problem are normal to each other. So sometimes this eigenvalue problem is also referred as eigenmode solution or normal mode solution. So to begin with our formulation of stability equation for incompressible boundary layer, first we need the laminar boundary layer profile. And for that, we are going to solve the self-similar boundary layer equation, which is also known as Blasius boundary layer equation. So there are the different types of stability analysis. So for current work, we are going to look into the 1D stability analysis, that is local linear stability. And by local, I mean that we solve the stability equation at each individual location as station 1, station 2, station 3. While in 2D stability, we call it as a biglobal stability analysis. In that, we feed the entire 2D mean flow, and for 2D mean flow, we solve the eigenvalue problem. But since in the 2D mean flow, there are several grades, and the eigenvalue problems are too expensive compared to the local linear stability, because it gives a huge eigenvalue problem, and that is expensive to solve. Considering 3D, which is also known as tri-global or fully global stability analysis, in this we feed the 3D mean flow, and this is further more expensive compared to 2D. So for now, for this study, we will be solving the local linear stability, where we solve the linear stability problem at individual streamwise location. So to begin with the stability analysis, as I said, we need the mean flow for the incompressible boundary layer. And to obtain the mean flow for the incompressible boundary layer, we will be solving this Blasius equation. So this is a Blasius equation, and we will look into how we are getting this equation. So to begin with the derivation, we will start with the continuity equation, and here we have the continuity equation for the 2D flow for incompressible. And here we have the x momentum and y momentum. We don't have energy equations since we are considering the energy incompressible flow. And to start with derivation, we transform this x independent x and y variable to xi and eta. We assume that xi is x and eta is some function of y in this form, where u infinity is a free stream velocity, this mu is this over here, nu is kinematic viscosity, and x is the independent variable. And then from the chain rule, we can express any derivative with respect to x in terms of xi and eta, and any derivatives of y, any derivative with respect to y in terms of eta. And we are doing this because we want to eliminate any derivative with respect to x and y in this equation with xi and eta, and that is our main purpose. So we can express the derivative with respect to x in this form, with respect to y in this form, and if we have the second derivative with respect to y, then we can express in this form. And you can always try this by considering this, and you can try this chain rule to make sure that you are getting this same. So yeah, so once we have this, we also define a stream function which is in this form. We assume a stream function in this form, and also to make sure that this stream function is a possible stream function, one can go and check this whether this particular stream function is satisfying the continuity equation or not. If it satisfies the continuity equation, it can be said that it is a possible stream function. So obviously you can try checking it by taking the derivative of this stream function with respect to x and y and satisfy, put in the continuity equation and check whether it is satisfying the continuity equation or not. Yeah, so we assume a stream function in this form, and we define here streamwise velocity. So when we take the, this should be y rather than x, this is a typo. So here we take the derivative of stream function with respect to y, that gives us the streamwise velocity, and when we take the derivative with respect to x, it gives the wall normal velocity. And by taking the derivative of stream function with respect to y, and this can be done by considering here we have the expression for what is going to be when we take the derivative with respect to y, how we can express it, and this comes from here. And we can express the u in this form, and this f prime basically comes from this equation over here. So you can put these variables and check whether you are getting this or not. And in the similar way, we have the derivative with respect to x here, and we have the expression for the x over here, how we are going to take the derivative with respect to x and express in the xi and eta, and that we do over here. Then we get this final equation over here, and I haven't written the smaller steps, but you can try by yourself by more simplifying it and checking it whether you are getting this or not. And once we substitute this u and v in the x momentum equation, we get the Blasius equation over here. And this is our Blasius equation that we seen on the top, which we solve using the fourth order Runge-Kutta method. And our goal is here, by solving this equation, to find the f prime. And this particular Blasius equation is solved within the two boundary. One boundary is on the surface, another is where the eta goes to infinity. So on the surface, we set the boundary condition for this particular problem as a f and f prime 0, while when the eta tends to infinity, we set the f prime as a 1. So once we solve this Blasius equation, we have the f derivative, f prime, and that gives us the velocity distribution within the boundary layer, and this information we will use for the stability analysis.